Hello, my name is Alan Hudson from the Immuno-Oncology Translational Network Data Management Resource Center. I also serve as Chair of Biostatistics and Bioinformatics at Roswell Park Comprehensive Cancer Center. Before we start the seminar, I just have a few bookkeeping items to go over. Questions will be responded to at the end of the presentations. Please put your questions in the Zoom Q&A box, not the chat box, the Q&A box. The audience can prioritize the order of questions by clicking on the thumbs up button. Closed captioning is available. The closed captioning for today's webinar can be accessed by clicking on the live transcript option in the Zoom menu at the bottom of your screen. Instructions are also provided in the chat box. With that, I would like to turn the proceedings over to our moderator, Dr. Eric Durbin. Dr. Durbin is an assistant professor in the Division of Biomedical Informatics at the University of Kentucky College of Medicine. He serves as director of the SEER Cancer Registry. He also serves as director of the Cancer Research Informatics Shared Resource Facility at UK's Markey Cancer Center. He has over 33 years of experience in population-based cancer surveillance, informatics support for basic clinical population and translational cancer research. Dr. Durbin's current research is focused on the integration of multi-omics data to support decision-making and precision medicine in cancer prevention and control. He also leads epidemiological studies exploring environmental, genetic, molecular, and other factors associated with high incident rates of childhood brain and central nervous system tumors in Kentucky and Appalachia. Dr. Durbin.
Thank you, Dr. Hudson. Thank you for the nice introduction. So first, I'd like to orient the audience just a bit. So from my perspective, in cancer surveillance, pathology remains the single most important resource in identifying a cancer diagnosis. Approximately 95% of all cases involve microscopic examination of tissue and reporting by a pathologist. Curiously, the vast majority of pathology labs still report their findings in narrative descriptions that are written or dictated by the pathologist. Therefore, rapid, reliable, and accurate classification of the cancer site, histology, behavior, and other factors from these reports has huge potential to expedite cancer registry surveillance, clinical trial matching, patient cohort discovery, and other functions critical to cancer research. For well over a decade, significant research in natural language processing has failed to sufficiently solve this challenge. Therefore, it is an honor to introduce today's Cancer Moonshot speaker. Dr. Heidi Hanson is the group lead of biostatistics and multi-scale modeling in the Computational Sciences and Engineering Division at Oak Ridge National Laboratory. Her training and experience in the fields of demography, statistics, familial analyses, biomedical informatics, omics, and life course epidemiology allow her to bring a unique set of expertise to building computational tools for population health research. She is currently the technical lead of the Department of Energy National Cancer Institute project entitled Modeling Outcomes Using Surveillance Data and Scalable Artificial Intelligence for Cancer, also known as the MOSSAIC program. MOSSAIC is focused on advancing computing, predictive machine learning, and deep learning models and large-cell computational simulations for NCI-supported cancer research. Please join me in welcoming Dr. Hanson to describe this exciting research that is showing significant breakthroughs towards solving this long-standing challenge.
Thank you, Eric. That was a great introduction. Let me get my screen up and we will go ahead and get started. Maybe. So as Eric mentioned, I am Heidi Hanson. I have been here at Oak Ridge. Let's see, hold on. There we go. Now
All good. Yep.
Okay, cool. So I'm Heidi Hanson. I have been at Oak Ridge for a little over a year now, and I have been very privileged to be part of the MOSSAIC project. So this project started before I joined the lab. It was one of the reasons that I joined the lab, and it has been absolutely fantastic being able to work with a team of scientists who are pushing this work forward. So before I get started in telling you about the MOSSAIC project, I want to draw this back to the Moonshot project, or the original Moonshot project. So I want you to travel back in time with me for a minute to a little over 50 years ago, where the, sorry, hold on one second. where folks were racing to land on the moon. And during this time, most of the computers were huge, taking up entire climate-controlled rooms. But at the MIT Instrumental Lab, they designed the Apollo guidance computer, which was a 1 cubic foot machine that had tiny donut-shaped metal cores that were strung like beads along a set of wires. Now, the importance of this is, number one, it was small enough to fit on it was small enough to fit on the actual machine going to the moon, which, and then it also had wire, it also did not fail. So they designed it in a way that it didn't really fail. So without the computers on board the Apollo spacecraft, there would have been no moon landing, and the calculations required to make the in-flight adjustments and complexity of the thrust controls and how it behaves as a system required calculations that were entirely out of the realm of human possibility. So harnessing the power of compute in ways that are previously unimaginable paves the way for conquering the implausible. And that's what was happening then. And that is the benefit of being here at Oak Ridge, is we are able to do something similar for all of our cancer data. So essentially, over the past few years, tons of data has been collected. So we're really in this unprecedented time for data collection, and also not only data collection and storage, but compute can now be done in exaflops. So what this means is, by building a national cancer data ecosystem, we can provide the infrastructure necessary for accelerating progress in cancer-related research. Rapid advances in computing and deep learning have resulted in advances in artificial intelligence that are beyond what most of us can imagine. I'm sure many of you have been checking out ChatGPT. So this is the prime time to develop data and compute-driven approaches for integrating cancer-driven research from basic research through clinical care and surveillance. So now, fast forward in time to the present, and here at Oak Ridge, we have a great compute system, one of the largest compute systems in open science, Frontier. And not only do we have Frontier, but we are able to handle private information or PHI data through the Citadel program. So Citadel is this framework that has the right security protocols, that allows for the data to be kept secure, so we can harness the power of these supercomputers when we're looking at cancer-related research and other medical-related research. Frontier can do about 1.1 exaflops per second. So just to give you an idea of the scale of that, if each person on Earth completed 1 calculation per second, it would take more than 4 years to do an exascale computer can do in a single second. So this is very great and also very powerful for what we hope to be doing in cancer-related research. So what is the NCI-DOE collaboration anyways? It was set up as a strategic interagency collaboration between the National Cancer Institute and the Department of Energy to accelerate cancer research using state-of-the-art scientific computing. The partnership includes the National Cancer Institute, as well as 5 national laboratories listed here, one of which is Oak Ridge, where I am sitting currently. The program was set up as part of the National Precision Medicine Initiative, and it started in 2016, and it continues to move forward. So there were 3 original pilot programs, one on molecular level analyses, one at cellular level, and one at population level. Our program, MOSSAIC, is the continuation of the population level program. And in all of the programs, are supported by Candle, a cross-cutting deep learning methodology framework that allows us to do the work that we do. So to date, there are 30 plus cutting edge, high impact AI and ML resources that have been developed out of this project as a whole. We are the MOSSAIC project. Dr. Lynn Pemberthy and Georgia Proce were the original PIs of the project, and they have been pushing it forward since the time of conception. So this population level pilot, as mentioned by Eric, has harnessed the power of large compute and deep learning to transform the way that we collect cancer pathology data, and it has provided the necessary building blocks for rapid phenotyping, case ascertainment, and reporting. Just to give you an idea of why this is important, so the public were able to witness firsthand the difficulty of making informed clinical and policy decisions about accurate and real-time data during COVID. This is a problem that permeates the public health system and affects health interventions, treatment decisions, and outcomes for cancer patients. For example, within the cancer domain, every year, a report on the state of cancer is released using the data collected by their surveillance, epidemiology, and end results program. I've pulled the results from this year's report for bone and joint cancer mortality. The reason that I pulled this information for you is that bone and joint cancer mortality has been increasing in males at a rate of approximately 2.3% per year since 2015. However, what you will notice is in this report that was recently pulled, I'm showing you statistics that only go up to 2019. That is because there's currently a lag between the time that the reports are received and the time that we are actually able to collate, harmonize, and release the cancer reports. And this is due to the difficulty related to collecting, phenotyping, and harmonizing data across all regions. This becomes an issue in different sorts of domains. One of them is rapid case ascertainment. So if we want to quickly identify individuals eligible for epidemiological and clinical research, and we want to make sure that we're giving everybody a fair shot at being research participants and also clinical trials participants, we need to have rapid case ascertainment. Right now, that doesn't exist at the national level. And so individuals aren't able to be identified and quickly enrolled in the trials that might help their cancer outcomes or help inform the science about cancer etiology. We also are unable to link it to near real-time environmental exposures or able to watch incidents and outcomes change over time. Now, anything in an incident that's changing quickly over time is likely due to some sort of change in the environment. And we are unable to monitor this in real time, which leads to a decreased ability for us to quickly identify rapid changes in cancer incidence and mortality rates that are due to these exogenous factors. And we are unable to develop the public health intervention strategies that could be used to prevent some of these increases. So that leads us to what the MOSSAIC challenge is. And basically, when Dr. Pemberthy and Proce set this up, they said they had the goal to create translational AI for better cancer surveillance and ultimately better cancer care. And through the process of the program, they have done that. So the project has, again, been charged with developing translational AI for better cancer surveillance. And I'm going to speak to you in a little more detail about the tools that have been built in the upcoming slides. And just to highlight, this is a really unique sort of collaboration. And in addition to being able to be here in a place where there's a lot of innovative science, DOE offers the ability for folks to work in interdisciplinary teams and really have a lot of resources to be able to answer the types of questions that need to be answered with the amount of data that we have for cancer. And so Oak Ridge Leadership Computing Facility has 2 of the 5 fastest supercomputers in the world that are dedicated for open scientific research. So if you're a computer geek, that's super exciting. And we are able to use that for the research that I will be showing you today. What's great is not only do we have this, but we have NCI, which brings their own unique resources to the table, including the pathologists and content experts to help guide the research so that when we are creating the algorithms, we're doing it in the correct way and that we are considering all the factors that actually need to be considered for this to be translatable science. And so not only are the pathologists helping us, we also have a large set of expertly reviewed and manually curated reports, and that's coming from the registrars at the SEER registries. We have data experts at IMS who are able to help us get all the data packages that we need to train our algorithms. And we also have ongoing data collection that we can do through the SEER program. And even more importantly is that we have nationally representative cancer data. So the SEER registries currently contributing data to our project are Louisiana, Kentucky, Utah, Seattle, New Jersey, New Mexico, and California. The SEER program is a program that is run by the National Cancer Institute, and it is an authoritative source of information on cancer incidence and survival in the United States. SEER currently collects and publishes cancer incidence and survival data from a population-based cancer registries covering approximately 48% of the US population. So this is extremely important to the algorithms that we are developing, because rather than just having one algorithm developed on a subsample of the data that's more likely select and cannot be scaled to the population level, we have the population level data at our fingertips and are able to make algorithms that are more generalizable and can scale to the entire US population. So what is a clinical pathology report anyways, and what are we doing with it? As Eric mentioned, somewhere upwards of 90% of all cancers are histologically confirmed. And when that is done, there's a pathology report that goes to that. So the pathologist writes a description of the cancer, and all of the information about that cancer is curated in one big, huge document, sometimes 10,000 words. So this very big document, in order for us to use it for cancer research, needs to be scaled down, and we need to abstract important information. So this abstracted information is just basically a summary of what is important for us in our research program from the report. And then in order to be used across many different places, there has to be some sort of common data format so that we can distill it down into tabular information. It can be used widely by folks. And so as we have the pathology report, information is extracted and then coded to a common coding data model. The relevant phenotype information is standardized to NACER reporting systems, and that's what we use for our gold standard label when we are training our prediction models. And that prediction is what we are trying to automate. So rather than having a trained registrar read through the report, abstract the information, and code it, our algorithms go in and automatically code that information, extract it from the reports, and code it so that we can decrease time from time of cancer report to actually being able to be used in cancer research from a matter of years to a matter of months or days, depending on how you slice it. So MOSSAIC has been developing these methods that accelerate the time it takes to process the pathological information, identifying and collecting new information to improve models, investigating foundational models, which I'm excited to tell you about in a minute, that have the potential to increase reproducibility and decrease the time that it takes to develop new models. We are also working on quantifying uncertainty in high-risk situations and developing tools that move us closer to near-time cancer identification and reporting. So what I'm going to do next is walk you through a couple of examples of each one of these segments and how my team is moving science forward in these areas. So I'm going to start with extracting information from existing electronic health records using scalable models for that clinical information extraction. We have been working over the past couple of months to make sure that the code base we're developing is reproducible, scalable, and sustainable. And what that means is we are designing a program that that is able to take reports of different types. So we have HL7, XML, CSV reports, take that information, ingest it, and process it in a standardized way so that it's cleaned, processed, and set into a database for our use. Now, if you're familiar with deep learning, machine learning models, At that point, there's still another data step that's required to be able to prep the data for training and testing. And so there's a separate segment of code that standardizes that information, and it pulls out the information in the way that we need it in embedding formats for what we're for training the models. And then we have our newest kind of set of code is a modularization suite. So essentially what that means is we have all of these different models. Some of them are in testing, some of them are actually in production, where we are trying to predict malignancies, phenotype classifications, pediatric cancers, report types, biomarkers, and recurrence. And this modular pipeline allows us to essentially pick which models we're going to be working on, or which models we'd like to wrap different packages around and pull from them in a very easy, efficient manner. So essentially it's ease of use, and it leads to the way that we've coded it leads to reproducibility. So I'm going to walk you through a little bit. I know data always seems to be the thing that people kind of don't want to talk about, but it is the most important part of the process, because the way that you clean and curate and document your data is extremely important in all things. As we all know, bad data in equals bad data out. And so we take this data processing part seriously. So what we essentially have designed is a new set of code that takes the data from the landing zone, or that first time when it hits our table, and processes it through in a very standardized way. And along the way, we also get automated profiling, so that we can see where there are issues within the data and fix those issues prior to them being passed into the model, and reducing the accuracy or the quality of our models. Once that is all done, we start to create the models. And we currently have 4 models that are in production. The first model is malignancy, whether or not that cancer information from the report indicates a malignant cancer. Phenotype classification, so we're predicting site, subsite, histology, behavior, and laterality from the text. For pediatric cancers, because they are a specific subset and have specific terminology surrounding them, we have a separate model that predicts pediatric cancer classifications. And then also report type. So is the information that we're seeing coming from a core, needle biopsy, or surgical biopsy? And this information helps us classify the reports in the proper manner. Our current production version is using a hierarchical self-attention network. So this is a similar for short, we call it the HISAN. And the HISAN is exciting because it uses a series of attention-based operations that generate fixed length vector representations of the data. And it does this in 2 processes, which is why it's the hierarchical. So first it does it in 10-word chunks. You get those representations, it passes it to the next level, where we get a document representation of what this looks like. And then at that point, we are able to pass that information, depending on the type of outcome we're looking at. We either use the final dense classification layer to use a softmax for single label classification, or a sigmoid for multi-label classification. So the HISAN model is an improvement of some of our past implementations that included CNN, and I'm going to talk a little bit about a new implementation that we're working on in a minute. But originally we started predicting these things on single reports, and within the past few months, we've released the case level context algorithm, and I'm going to talk a little bit about that next. But what that allows us to do is essentially look at an entire case and merge the reports together for an entire case, and not just a single report at a time. So this case level context, or multi-document contextual model, as I mentioned, combines information across court reports and allows us to make more accurate predictions. So we are able to really analyze each pathology report in the context of the other information that we have about the patient. And we found that this type of model improves our prediction substantially. And this is what the most recent release of our information extraction model uses for predicting the different phenotypes. So now I'm going to shift a little bit and talk about abstention and uncertainty quantification. And it's actually not that big of a shift, but what happens if you know classification models really well, you know that when I make a prediction on a certain report, I'm going to predict some value. And that means that there are going to be values that I'm pretty confident in and values that maybe I'm not so confident in. And for certain scenarios, that's completely fine. In the medical field, we don't want predictions that we're not confident in. So these are high-risk scenarios where my bad prediction has high consequences. And so in order to handle that problem, we've worked with Los Alamos National Laboratory, and they've developed what is called the deep abstaining classifier. Abstention essentially means that you are declining to classify during training and inference. So when you are predicting on that record, if it is not of high quality, that rather than predicting a type of cancer, you predict to abstain on that prediction, and that report can be manually reviewed. So the DAC is unique because it learns rather than just setting some a posteriori percentage point for where we believe that prediction. It learns features that are indicative of unreliable or uncertain predictions, and then it actually uses that information to predict when a report should not be trusted. And we do not use that information when it is reported out to the SEER registries. The DAC is implemented in multitask pathology classifier API, which is our production version of this. And the samples that are not abstained during inference are auto-coded. We currently have it set at 97% accuracy, and we're predicting at 97% accuracy with the case level context model, somewhere in between 22 and 30% of our path reports. The high level of accuracy might make you cringe depending on what your field of study is. And the great thing about DAC is this can be tuned. So we've set it at 97% accuracy because that works for our scenario. But in other scenarios, let's say for research purposes, it may not be as important to have a high confidence in that prediction, and it can be tuned to a lower level. Outside of not predicting on reports that we're not confident in, we also are involved in identifying ways where we can interpret the information or the models themselves to make sure that the models that we've built are accurate. So Lime is one way that we use to do this. Lime is not a workflow built within our shop, but it is one that has been integrated into our workflow by Los Alamos National Laboratory, and it's an important addition. Basically, it allows us to identify features that are important to our model predictions at the report level. So Lime is a local interpretability method. And what I'm showing you here on the left is a figure that shows you examples from a Lime report. So in this case, we were looking for words that were important predicting the type of cancer, lung, breast, or prostate. And then that abstention class that I was talking about earlier, where it is unable to predict. And we find that the relevant words make intuitive sense, which is very, very good for us. So we utilize this method as an important step in identifying systematic errors in the data that could lead to unreliable predictions. As I said, it's part of our workflow. And so, for example, in a past implementation of this, we use this tool to look at how our model's doing and if there's anything weird going on. And we identified an errant XOD character, which is an escape character, and is not visible when you are looking at a report. But the model was picking up on this character, and there was systematic bias in that all reports of one type contained that character. All reports of another type did not, because of the way the reports were processed. So doing uncertainty quantification and interpretation allowed us to identify the issue, correct the issue, and then retest our model's results to make sure that such issues did not exist and that the models that we were training made sense. Lyme is local, so when we run it, we have to look at it on a report by report basis. Sometimes we aggregate it up to look for trends in the data, but it doesn't give us a good look at interpretability at a global level. So what is our model doing overall? And we're very interested in global explainability of our models as well. So we've been working, one of our scientists here, Adam Spanis, has developed a topological approach to global explainability. And this allows us to, again, just look at the results of our model and how our model is predicting certain features to make sure that everything looks reasonable and that our model should be performing correctly in this problem space. And the beautiful thing about the method that Adam has developed is it can also be applied to other problem spaces in deep learning models. It's not only applicable to what we are doing here in this project. Another important step in what we are doing, and a reason why the NCI partnership is so fantastic, is we are collecting data and developing new APIs. So we started with the information extraction API, and that was going very well. We have a reportability API that's great. We wanted to develop recurrent an API that could predict recurrent metastatic disease because it's not systematically collected or has not historically been systematically collected at the population level. And we wanted to develop an algorithm that could do that. We also would like to develop algorithms that can predict biomarker status. In order to do that, we need data collection because that data doesn't exist. So with our partnership with the NCI, we were able to establish a recurrence and metastasis truth data set. So the new path reports collected from cancers diagnosed from 2001 on the data collection began in the first of 2021, and that data collection has been ongoing, and we have to date collected over 50,000 reports, which is great for us because these are manually curated data that is available through the SEER registries and allows us to help train our new models on recurrence and metastasis. So this has been a great collaboration. And now that we have this data, we are able to develop the predictive models and hope to have a new model that will be able to predict recurrence or metastasis in SEER data. We also are working on extracting biomarker status from pathology reports. We've started with ER, PR, HER2, KRAS, and MSI. We trained the ER, PR, HER2 models using breast cancer cases, KRAS, MSI using colon cancer cases. And then we found that we had very good model performance, and you can see the F1 scores on the right-hand side. The model performance for both the ER, PR, HER2 for all of the biomarkers has been great. MSI is not quite as good, and we are working on further fine-tuning that model. So we took the models that were performing well and trained on breast or colon cancer, and we wanted to see if we could use those models in a sort of a knowledge transfer approach to identify HER2 and KRAS biomarkers in non-breast and non-colon cancers. We have an ongoing study where we are looking at about 1,400 reports that were reviewed and annotated by pathologists to identify whether or not our predictions were correct in these models. For KRAS, there is high accuracy. HER2, there is high accuracy in certain cancer types, and we are working on fine-tuning it in other cancer types because the performance is not quite where we want it to be. So these are beta models, and we are currently working on improving the algorithm and hope to extend it to other biomarkers soon. One of the more exciting parts, although it's all exciting, of the research that we are doing is currently being developed by Mayanka Chandrasekhar, John Gownley, and Isaac Lingas. Sean Gao was part of the development as well, and he has moved on to work on other things. So this is work that was started by them, and is being pushed forward by them. And we hope to transition into some of our production models very, very soon. So this is transformer model. The new model architecture that I'm talking about is a transformer model. And this model is something that there's been a lot of buzz about lately. It's a very accurate model. One of the limitations for using it in clinical text is very long. So transformers models were originally built for short text, tweet-like text, and they didn't work effectively within our problem space. That has since changed. And the exciting part about transformers is they can be conceptualized as a foundational model. And the reason that it can be conceptualized as a foundational model is that first step of training is unsupervised. So there is no task that you're predicting on your pre-training. You're using bidirectional encoding and a task agnostic and computationally intensive model to basically learn the patterns in the text. You have all this text data, you're able to learn the patterns. And then it's the second step, or the fine-tuning step, that allows you to predict what you want out of the text. Now, that first step is very computationally intensive and is what takes all of the big compute. The second step, not so much, and it's a lot faster. So the beauty of this foundational model is we can have all of that information pre-trained, and then we can switch tasks fairly rapidly, depending on what we want to look at. And so what we have done is we've started with our first information extraction tasks: site, histology, laterality, subsite, and behavior. And we've expanded to have the same pre-trained model used for fine-tuning for prediction of biomarkers and childhood cancer classification. And we expect to try it on other tasks as well. So again, it's the interoperability that is really fantastic and exciting to folks. And it's a big step in our research, and we're excited to almost have it ready for production. So you can see in this slide the performance of the transformer model on path extraction tasks. It is better than our implementation model now, or our production model now, which is the HiSAN. The HiSAN can be seen in the gold bar, and the transformer results, depending on the way that we are running them, can be seen by the blue bars. And you can see here that we are much better at certain tasks than others. Perhaps our least well-performing models for histology. And the exciting part is this is one of the most difficult tasks for us to predict, and the transformer model has improved upon that substantially. So very exciting work coming out of scientists in our group, and we hope to release it soon. So outside of the models that we're developing and all the fun science and compute that we get to do here, there is another very exciting component, and this is the fact that this project is truly translational. So the results and the APIs that we are developing are already being used in real world settings, and we have plans for increasing the use in the future. So what this means is we are truly using the tools that we're developing to enable near real-time cancer reporting and case ascertainment systems. There's still a ways to go, but we are very optimistic about where we can be over the next few years with regards to real-time cancer reporting and extraction from pathology reports. So just to give you an idea of how this is actually being used in the real world, I'm going to walk you through what we have deployed now. So in May 11th of 2021, the initial deployment was in Georgia. And currently 11 SEER registries, I'm sorry, that number is actually higher now. This was from an older slide. I believe it's up to, it may be 16 SEER registries and one non-SEER registry. I'm gonna have to fact check myself on that. Use this in the clinic, or sorry, in their registry to predict the different tasks. Other registries that do not process paths in SEER DMS or not using SEER DMS may have the potential to use this in the near future, given the code base that we are building. And then outside of that, we are doing, outside of the deployment, we're doing a manual QC of 10% of the reports that are auto-coded, so that we can check to make sure that the algorithm is working correctly, and we can fine tune it and correct it if there are issues in the predictions. There are approximately 3 million reports reviewed annually, and of those 3 million reports, 22.5% of the records are auto-coded with 98.1% accuracy. This has been moved into a near-time reporting pilot, where NCI started their first real-time reporting pilot in November of 2022. The SEER site recode of non-auto-coded reports. So what we're predicting is a fine level, smaller level of specificity. So the exact site or subsite of the cancer and the histology. SEER site recodes are more general. So it's essentially taking that information, rolling it up into a higher classification, which makes it a bit of an easier classification task. When we're not trying to predict at the specificity needed for cancer collection, we are able to auto-code a large percentage of the reports with 97% accuracy. And I believe I don't know the exact number on that, but it is a very high percentage, upwards of 70%, I believe. We are also able to work to quantify temporal shift. We've been working to quantify temporal shifts in accuracy and bias in algorithms. So what can happen is once you create an algorithm, as the data shift, as things shift, the model no longer becomes is no longer as accurate. So that accuracy shifts over time. We are doing quantifying what those temporal shifts look like. We haven't seen anything large on our side, but we are keeping that in mind and working on correcting any algorithm bias that might exist. Another exciting thing going on here is that we have been working on federated learning with differential privacy. So as I mentioned, Citadel allows us to handle private health information in a secure way. And one of the big barriers to having national level healthcare reporting is the fact that centers don't want to share data with each other. So under this plan with federated learning, the benefit would be that each one of the centers or institutions would not have to share data, but data would be able to be kept in a secure silo that doesn't have to speak to any of the other data. And that the model could be trained using the data in those silos. The gradients are passed to a global model. Training is done, passed back, and through this iterative process, you are able to train a model as if you had all of the data pooled in one central repository. So that is something that would really improve population level health predictions and combining data from across the entire United States. One of the things that folks don't mention, you hear federated learning a lot, it's a big buzzword, is the fact that passing of those gradients around in a non-secure way doesn't really help prevent the leakage of PHI data. So we are working on differential privacy methods to protect that. So essentially what differential privacy is, or epsilon indistinguishability, is you can inject noise to an amount that gives you very high privacy, but because you're injecting noise, you're going to reduce your accuracy. Or you can inject a small amount of noise and keep high accuracy, but potentially reduce your privacy. What's unknown in our world is what this privacy accuracy trade-off looks like when you're dealing with institutions that do not have evenly distributed data. So different types of institutions will have different types of text outcomes. And so we've been working on what does this look like in a real world scenario implementation, and how can we set up tools that allow folks to do this who aren't super savvy when it comes to IT sorts of problems. So you have to be somewhat savvy, but making this easy for users who do not have a strong HPC background. We have been able to come up with a beta version of this and currently are working on it. But essentially what we are able to do is within Citadel, we are able to train a model using data across multiple sources and maintain some sort of privacy when doing that. So in the upcoming years, what we hope to do is open this up to other institutions so that they can benefit from having large amounts of data without the cost of pulling those data in at another institution or centralized repository. This is something that we will hopefully be moving forward on over the next couple of years, and we are very excited about this move, about this project. So just to summarize where we've been, the MOSSAIC project is part of the broader objective of the NCI to build a national cancer data ecosystem. We have been doing multiple things in order to move this along. First, we have been extracting information from existing electronic health records through the use of AI and deep learning. And then we have been standardizing data infrastructures so that we can make sure that once we have developed this code, it can be released to the broader public. Individuals can use the code for their own training. Not only that, they can potentially benefit from the use of it within a federated environment. We are developing new transformer models or foundational models to further increase reproducibility and the ability to train across multiple different types of questions. We are developing new ways for uncertainty quantification, verification, and validation of our models, which is very important in a high-risk healthcare setting. And then we are also working with NCI and the SEER registries to make this translational tool that is actually affecting population health now. Our next steps to help move forward precision health is to continue to improve the auto extraction rates with improved deep learning methods. So here at DOE, we are constantly looking into what are the new methods and how can we improve upon what we have already done. That's what makes us very excited, and we are looking forward to continue to move that forward. We are also working on new ways for global explainability with Los Alamos National Laboratory for increasing the understanding of model performance. We are building tools for predicting recurrence and metastasis in cancers, which is currently not done at the population level. We are refining our prediction models for recurrence, metastasis, and biomarkers. And we are also hoping to utilize linked residential history data to continue to understand environmental exposures and health outcomes. Now, as you know, I've been here for less than a year, and that is not this is not a one-person job. So I've been here for about a year, and this is not a one-person job, but it's a job done by an entire team. And so these are all the folks contributing to the project and doing all of the great science that I presented here. So I'd very much like to thank all of the scientists here at Oak Ridge and all of our collaborators at National Cancer Institute and IMS, as well as the great work that the scientists at Los Alamos National Laboratory do. This is truly interdisciplinary science at its best, and I'm very excited to be able to be working with the team. And with that, I will stop for questions.
Hey, Heidi, that was just a great talk, and just so many interesting aspects of this research. So we've had a lot of great questions that have come in. I'm actually going to start with my own question, and it's a little bit of an insider question. So we've observed really good progress towards classifying between 20 and 30% of path reports with pretty high accuracy, which is really important. But these appear to be for pathology reports from the most common cancer sites. So what's the strategy for improving performance on less common sites?
Yeah, you are spot on. So we're really good when there's lots of data for the most common cancers. It becomes less great when we're looking at the minority classes. So we have been playing around with a couple different ways to deal with this. Again, one thing that will benefit is the transformer models, where what's causing us to be unable to auto code is histology a lot of the time. So there are a lot of histological classes, they're difficult to classify. And that is one thing that makes it very difficult for us to classify. So the transformer models will improve on some of those histological classifications. We are working on different methods for data augmentation that may be able to help in the cases of the rare classes. So part of the issue is that you have it when you only have a few classes and you're training across everything, the model tends to want to predict toward the majority classes, right? Because there's a benefit there. So we're playing around with different ways of data augmentation. We're not having as much success with that, some success. So we're looking into other methods as well. Some of the other approaches that we're considering are active learning approaches. And we're also looking into other, maybe new, more novel ways of really dealing with this minority class problem with the big models.
Excellent, thank you. So we have some early questions that are related to Citadel. So the first question is, has Citadel been used for medical images such as MRI scans? And a follow-up, who can use Citadel and what's required to set it up?
Yeah, so Citadel can be used for MRI scans and not MRIs. It can be used for MRI scans. It is used for WSI images currently within this project, and there are other projects that can use it as well. So you do not have to be a DOE investigator. You can go through for an insight proposal, and there you can look a little bit more on the webpage on how to do that, or feel free to email me and I can point you in the right direction. But there are processes that require, you have to go through processes in order to use it, but it's not an unsurmountable task to be able to use the resource.
All right, great. So David Axelrod writes, what good is rapid analysis of pathology and exposure if cancer progression may take decades? So once surveillance data is available, it may be too late.
Yeah, that's a fantastic question. So you're spot on. If you're thinking about environmental exposures, there's generally some sort of latency period. So in the case of like arsenic, you're looking at maybe a 30-year latency period. So, hey, you can have rapid case ascertainment with those pathology reports, but the exposure that actually led to the cancer in question was 30 years ago. One of the great things about the SEER registry is they have been working to get residential history information, and they can go back now into around 1990 is my understanding, and have that residential history information. With the benefit of rapid case ascertainment, you can start to look at residential history and how past influences or past exposures may lead to changes in cancer incidence or mortality at the current point in time. The other thing to think about is folks always want to tie environmental exposures to incidence, but environmental exposures are important throughout the entire life course. So generally, individuals who are in high exposed environments prior to cancer diagnosis, not generally, but oftentimes or sometimes those folks return back to those high exposure environments after cancer diagnosis. So it's not just that high exposure environment led to my cancer incidence, but that high exposure environment can lead to poor outcomes as well and higher mortality too. So identifying folks that are at even more of an increased risk for adverse outcomes early on or at time of incidence would be important as well, not 2 years after the fact.
Excellent, excellent. So there are a couple of questions about the source data that you're utilizing. And so the question is from Juan Mo, are the pathology reports from clinical EHRs in a PDF format or from laboratory information systems where the pathology reports are more structured? And a follow-on question, to what extent are you using the CAP checklist elements in this research?
So basically, it's not PDF, it's electronic. So we're not doing any OCR on it. We're getting these reports in electronic version. They're coming in a variety of versions, and IMS does a lot of that data processing for us. So before the reports even get to us, there's this step where the data go through IMS. They're pulling out or extracting certain records for us or passing the HL7s to us, and we're capturing the text part of the document. So I know that there's abstract or maybe cheats in some of the data where the site and histology are provided depending on what kind of the structure of the report looks like. That's not consistent across all places. And so we're not using that information, but we are using the clinical text information that's coming through that electronic version of the pathology report. And if that didn't quite make sense, you can call me on it and I can try to explain it in a little bit better way.
Yeah. So we've also seen a couple of FDA-related questions. So Leah asks, how will this affect the cost of cancer diagnostics, and will the FDA be able to regulate this technology?
Sorry, can you repeat that first part again?
Yeah. So how might this affect the cost of cancer diagnostics? And is this something that the FDA in the future may be regulating?
Wow, that is a great question. And I have not given it any thought and don't know. I'm not quite sure how to answer the question. Yeah, I don't know how to give an intelligent answer to that question.
Yeah, and if I could comment myself, at this point, this is not, the research really isn't involved in clinical diagnostics, although that could be the future. So a question in my mind is, could we envision a future where this technology has been implemented and a pathologist is being assisted by such methods in the midst of reviewing a case and creating their diagnosis?
Yeah, I think thinking about how this can be used across many different sorts of venues is very interesting, and that it definitely can be done. So if you're thinking about how to make information more readily available in the clinic, or having a summary of information pulled up at the doctor or within the clinical trials, I think that becomes very interesting. With clinical trials itself, extracting some of this information for rapid case ascertainment leads to the ability to maybe flag patients eligible for clinical trials, and the information can be passed to the doctor. But I don't see it necessarily being used quite yet for clinical diagnostic purposes, and therefore I don't know that it would have to go through any sort of FDA regulation.
Great. So Rayo has a question that actually was on my list, and the question is, by any chance, do you have the slides used for generating these pathology reports in the EHR in a digitized fashion? And the question really is, wondering whether this could be used possibly for training or validating the tools and algorithms, or improve the image classification to ascertain the case for the stage. So if you actually had access to a digital image of the slide from the path report.
Yeah, that is such a great question. So we do for some of the childhood cancer cases. So we are on a project that is looking at, that has both access to the whole slide images and the pathology reports, but it's for a small number of records, a very small number of records. So we are hoping to capture more image information, and would like to do something just like that, where we're able to combine imaging data, pathological information, omics data at some point in time, EHR data, as much data as possible to improve predictions.
Super. All right, so we have probably time for just one or two more questions. But Ashish writes, I was wondering if you had multiple pathology reports for the same patient over time, or in a temporal fashion, and could we try to predict disease progression and prognosis based on progression trajectories of similar patient disease progression trajectories? So if you had path reports over time, do you think you could predict progression?
Yeah, another question I absolutely love. So the answer is yes, we do. And I think that would be a very interesting way forward. So right now, the multiple pathology reports are used in a contextual fashion for a certain window of time. So if you have, let's say, 4 pathology reports within 30 days of each other, 300 days of each other, whatever we set that to, can that information be used to improve our predictions? But we haven't yet looked at trajectories of progression. And that would be something that would be beautiful to do. Even better, combining those multiple pathology reports with electronic health record data, so we could really look at progression of disease over time.
So I think that's probably the time to wrap it up. Thank you, Dr. Hanson, for an excellent talk. We will get you the unanswered questions, and if you'd like to respond to those at your own time, that'd be great.
Absolutely.
Thank you, Dr. Durbin, for a great moderation effort. And I'd like to remind everyone of our next Cancer Moonshot Seminar Series on February 23rd. Dr. Davis from Translational Genomics Research Institute and Dr. Smith from Dartmouth College will be talking about advancing cancer outcomes through implementation science and participant engagement. Thank you, everyone. That was great.
Thank you.
U.S. Department of Health and Human Services, National Institutes of Health, National Cancer Institute, cancer.gov, 1-800-4-CANCER.